Hello, this is Jonathan Ventura, and I am pleased to present our work on absolute pose from one or two scaled and oriented features. Our work is on image-based localization, where we assume that we have a set of reference images with known camera poses and a model of the scene. Our task is to determine the rotation and translation of a query image. The most widely known solver for this problem is called P3P, or perspective 3-point. Given at least three 2D observations of known 3D points in the scene, we can estimate the pose of the query image. This is a thoroughly studied problem with a long history, and P3P solvers are currently used in many computer vision applications. P3P uses only feature locations to compute absolute pose. In our work, we were interested to explore how feature scales and orientations could be used to improve image-based localization. Feature scales and orientations are often computed as part of the feature detection process, or can be estimated separately using traditional algorithms or learned methods. While recent work has mainly focused on relative pose estimation from scaled and oriented features, relatively little work has explored absolute pose estimation with such features. We aim to compute the absolute pose of the query image given one or more scaled and oriented feature correspondences between the query image and reference images. For each correspondence, we know the location of the observed 3D point and its surface normal. In our work, we derive novel constraints on absolute pose from scale and orientation features based on analysis of the underlying local affine transformation. Based on these constraints, we developed two new minimal solvers for absolute pose from one or two feature correspondences. In synthetic data tests, we established the numerical stability of our solvers and their performance under various types of noise. In our real data tests, we demonstrate an improvement in recall and runtime when integrating our solvers into an image-based localization framework. Our starting point is the affine correspondence constraint introduced in our previous work presented at ICCV 2023. In this work, we derived an expression of the 2x2 local affine transformation matrix A in terms of the relative pose between the reference and query images, the 3D point, and its surface normal. Baráth and Kukelova derived two constraints relating to affine transformation and the feature scales and orientations. The constraints ensure that the feature scales and orientations are consistent under the affine transformation. It is also possible to eliminate scale from the constraints to obtain a single constraint involving only the orientations. By plugging in the affine transformation matrix form derived previously, we obtain constraints from the feature scales and orientations on the query image pose. Our P2 ORI solver solves for the absolute pose of the query camera using two oriented point correspondences. Our UP1 SIFT solver is an upright or gravity-aware solver, meaning that we assume knowledge of the gravity direction for the query camera. This reduces the rotational degrees of freedom so that our solver requires only one oriented and scaled point. Although the name references the classic SIFT feature detector, the solver can be used with any feature scale and orientation estimation method. For our real data tests, we use two benchmark datasets. The first is the Cambridge Landmarks dataset, which contains smartphone images of several outdoor scenes. The second is the Aachen day-night dataset, which includes smartphone images taken both at daytime and night, and thus provides a greater challenge for image-based localization. On the Cambridge Landmarks dataset, P2 ORI and UP1 SIFT achieved higher average recall than P3P and the P1 AC method, which uses a single affine correspondence. Similarly, on Aachen day-night, our methods outperformed previous methods in terms of recall. Finally, the average graph cut ransack timing was faster when using our methods. To summarize, we derived novel constraints and minimal solvers for absolute pose from scaled and oriented feature correspondences, and achieved higher recall and faster query times on benchmark datasets compared to P3P and other baseline methods. We are curious to see how our methods could be extended to uncalibrated, generalized, and non-minimal problems, and to explore their integration into structure from motion and SLAM systems. Our code is available on GitHub. Thanks for listening.